Hello! What I'm going to do today is I'm going to do a two-object problem involving circular motion. So this is something in the harder forces range. The objective with harder forces could involve circular motion, it could involve springs, often involves two objects, any combination of those. So here's one that involves circular motion, which is a little bit harder than our typical circular motion problems. We have two masses connected by a string. The string passes through a hole in the center of a flat table. The lower mass hangs steady with no motion, while the upper mass moves in a circle on the table. There is no friction between the table and the upper mass. That top mass is 800 grams. The hanging mass is 1,500 grams. What is the period of motion of the upper mass if it swings in a circle with a radius of 32 centimeters? All right, so what does this thing look like? We have a table, and there's a hole in it, and we have a mass going around in a circle. So we've got a mass, and it's going to go around in a circle. So, whoop. And then the other end is connected by a string to a second mass. So that's kind of what I got. So I'm going to call this mass 2 and this is mass 1. We know the mass of the upper one, the top one, is 800 grams. But I look at that 800 and say, got to convert to kilograms. 0.800. Mass 2 is 1,500 grams, which is 1.5 kilograms. No friction. We want to know the period of the motion. If it's swinging in a circular motion with a radius of 32 centimeters. I'm going to convert that to meters right away. All right. We've got this circular motion attached to a hanging mass. This isn't looking all that different from the lab we did for circular motion, where you spun it in a circle, but we were holding this one constant. We know the two masses. We want to know the period. And now here we have to be very careful. Because if you looked at this problem without me asking what is the tension, oh, I just did it. What is the period? T usually means tension. So we have lots of capital T's going around. We are looking for the period, which is capital T, but we're also going to have tension, which is capital T. So we have to keep very close track of which T we're dealing with, because we have multiple ones. That's one of the reasons this is a harder problem, is we have two capital T's and two masses. We got to keep track of which one's which. All right, we have a force problem, so I'm going to do force diagrams, and I have two objects of interest, so I'm going to do a force diagram for both of them. For number 1. All right, so this one's swinging around in a circle. There's no friction on the table. So when it's at this point right here, what do we have for forces acting on it? Well, the table is supporting it. The earth is pulling down on it. Oh, well, M1G. And the string is pulling it to the right. So this is tension. That's all we got. What direction is the acceleration? This is going in a circle. Centripetal acceleration always points towards the center of the circle. Bloop, it's going that way, which had better make sense. It better be consistent with our force diagram. If you said acceleration was this way but had tension going that way, that would be a problem because the tension is going to be what's causing that acceleration. There is our first force diagram. Our second force diagram for the hanging mass, well, that's pretty easy. We have our hanging mass, the earth pulling down. We have our tension going up. And this one, it's holding still, there's no acceleration. All right, what next? Well, I can see that this one's pretty straightforward. If this is not accelerating, then all the forces are balanced, which means tension equals M2G. So tension equals M2G. There's an equation for tension relating to mass. This one, if I do my XY chart, I've got 0 plus N, 0 minus M1G, plus tension, and 0. In the X direction, I've got my tension equals M 1 times my acceleration, which is centripetal. In the y direction, there's no acceleration up, down, so my normal equals m1g. Okay, 3 equations. And despite what it looks like, this t is not here anywhere. So how am I going to get my t period, my time for 1 revolution? All right, circular motion. If we go back and think about it, circular motion, we have this equation. Velocity is 2 pi r over the period. I know my radius. I don't know my velocity. But I can relate velocity to radius and centripetal acceleration with this one. And I do have an equation for centripetal acceleration. So if I'm looking for period, I have that. I need v. I can get v from this if I have AC. I can get AC from this if I have tension. How do I get tension? Well, I have another equation for tension here, relating it to weight of the second object. I have enough information. I can do it. Do we use this one at all? Nope. It's not wrong. That's perfectly true. The normal force in this case is equal to the weight of object 1. Just doesn't help us. So I'm going to give myself some space by getting rid of that one. Okay, how should we do this? Let us set the 2 tensions equal. I have an equation for tension and an equation for tension. We know tension equals tension. So m1 times AC equals m2 times acceleration due to gravity. And again, I want to solve for AC. AC equals m2 acceleration due to gravity over m1. Don't cancel those masses out. If you say mass and mass, it'll be wrong because they're not the same mass. One was 800 grams, one was 1500. So don't cancel those. Keep those subscripts. We now have an equation for AC. We can solve for that if we want, or we can keep throwing it in to further equations. I like to sometimes do the math right at this point just to, well, really so that when you solve the problems, I know if my answer matches with your answer. Mass 2 is 1.5 kilograms. Acceleration due to gravity, 9.8 over mass 1, 0.80. My centripetal acceleration is 18.4 meters per second squared. All right, so there's my first relationship. Now I know AC. I have AC, and I have my radius. I can solve for velocity. Velocity is going to be the square root of radius times AC. Radius is 0.32. Ooh, squeaky marker. 18.4. And if we do that, the velocity of this thing as it's going around, velocity is 2.43 meters per second. Next step is done. Now I have velocity, I have radius, I can get my period. So the period, now this is the t that's the period, not that t or that t or that t. Flip those two around, it's 2 pi r over my velocity, 2 pi times 0.32 over velocity, 2.43, I get a period of 0.83 seconds. Is that a reasonable number? Well, what does that mean? What is the period? The period is the time to go once around. So a little bit less than a second for it to go around a circle that is about 32 centimeters. 32 centimeters is about a foot. So it's going in about this, about 2 feet across, 60 centimeters in a little bit less than a second. I would say that's reasonable. Seems quite reasonable to me. The other way to think about it is this is the seconds per revolution, which you can invert to get its 1.2 revolutions per second. So in 1 second, it'll have gone around once and a little bit more. Did we answer the question? The question was, what's the period of the motion of the upper mass? We've got it. It's reasonable. The units came out for seconds. And I'm just going to remind myself, this is the period. I mean, the unit should tell me it's the period, not the tension, but just period. So this is an example of a two-object problem using circular motion. A little bit harder than our standard circular motion problems, so this would count towards the objective on hard forces. Anything else I want to say about this one? So be careful with your units, and be careful with tension and period. That one in masses. We have multiple masses and we have multiple T's going around here. So that's a couple of things that you should be careful of when you're doing this type of problem. Don't go madly canceling stuff out unless you know for sure they are the same thing. Other than that, I think we did a good job here. All right, good.